Which of the following assumptions are correct for cold rolling? So the question is about cold rolling and its assumptions. So here the first assumption is the material is plastic. As in the cold rolling, it is plastic deformation. So the material is in plastic state. That is correct assumption. And second assumption is the arc of contact is circular with radius greater than the radius of the roll. So the arc of contact is circular, that is true. So arc of contact is circular with radius greater than the radius of the roll. So this radius is greater than the radius of this roll. So that is correct assumption, because you can see here the arc of contact is circular with the radius greater than that the radius of roll. That is a standard assumption. So thereby statement 2 is correct assumption. And third one is coefficient of friction is constant over the arc of contact. So the coefficient of friction mu is constant over the arc of contact and acts in one direction throughout the arc of contact. The third assumption is wrong. So thereby we can conclude that 1 and 2 are correct. That is option A is correct option. Consider the following statements. Roll force in rolling can be reduced by. So this is about roll force in rolling. First statement is reducing friction. So by reducing friction, they are telling the roll force can be reduced. That is true. And next, using large diameter rolls to increase the contact area. So when the contact area is increasing by the large diameter rolls, the friction is also going to increase. So thereby it will not reduce the roll force. So statement 2 is wrong. Taking smaller reductions per pass to reduce the contact area. So when we take the smaller reductions, the smaller reduction is thickness per pass. So for every pass we are taking smaller reductions. So thereby to reduce the contact area. So when the reducing contact area is happen, at that case the roll forces and the friction will be reduced. So thereby statement 3 is also correct. So we can conclude that option C is the correct option. In a rolling process, the maximum possible draft, that is delta H maximum, defined as the difference between the initial and final thickness. Initial thickness minus final thickness of the strip of the metal sheet or strip mainly depends on which pair of the following parameters. So they are telling this maximum possible draft is depend on which pair on the given parameters. So the first one is strain. So we have maximum possible draft delta H maximum equal to mu square into R, where mu is coefficient of friction between roll and work and R is radius of roll. So the given first parameter is strain. There is no strain parameter involved. And next, strength of work metal. So we can see here maximum possible draft. There is no strength of the work material. And next, roll diameter. So roll diameter is R, that is radius, diameter is D. So that depends on the roll diameter. Roll velocity. So there is no velocity factor in this. So that means this is also wrong. Coefficient of friction between roll and work. There is mu, that is the coefficient of friction between roll and work. So here R and T are correct parameters. So thereby option B is the correct option. In a rolling operation using rolls of diameter 500 mm. Roll diameter is given, that is 500 mm. If a 25 mm thick plate cannot be reduced to less than 20 mm in one pass. So the 25 mm thick plate, it cannot be reduced to 20 mm in one pass. So that totally means maximum possible draft is 25 minus 20, that is initial thickness minus final thickness, that is 5 mm. The coefficient of friction between the roll and the plate is. So we need to find the value of mu here. So we know already maximum possible draft delta H maximum equal to mu square into R. So already R value is given, delta H maximum is also found. So once we put it in the value, we get 0.1414. So 0.1414 is the answer. A 300 mm thick slab is being cold rolled using a roll of 600 mm diameter. So we have 300 mm thick plate which is being cold rolled using a roll of diameter 600 mm. So that means radius equal to 300 mm. If the coefficient of friction is 0.08, so mu is 0.08, the maximum possible reduction in millimeter is. So the maximum possible reduction is nothing but maximum possible draft. Since all the values are given here, so we can directly put it in the equation. So we get 1.92 mm. So answer is 1.92 mm. A 4 mm thick sheet is rolled with 300 mm diameter rolls to reduce thickness without any change in its width. So we have a sheet of thickness 4 mm which is being rolled with a roller diameter 300 mm, and the friction coefficient at the work roll interface is 0.1. So the coefficient of friction is 0.1. The minimum possible thickness of the sheet that can be produced in single pass is. So they are telling to find the minimum possible sheet thickness after rolling. So this is before rolling, this is after rolling. We have to find this value. So as we know, maximum possible draft is equal to mu square into R, and draft equal to initial thickness minus final thickness. Since the all values are given except minimum possible thickness, so once we put all the values, we get the minimum possible thickness is 2.5 mm. That is option C is correct option. The thickness of a plate is reduced from 30 mm to 10 mm. So we have a plate, assume this is the plate, its thickness initially it was 30 mm and it has been reduced to final thickness of 10 mm by successive cold rolling passes. So there is cold rolling using identical rolls of diameter 600 mm. So the diameter of rolls is 600 mm. Assume that there is no change in width. So the width of the plate will not change. Width of the plate is constant. If the coefficient of friction between the rolls and the workpiece is 0.1. The coefficient of friction is 0.1. The minimum number of passes required. So we need to find the minimum number of passes to reduce the thickness of 20 mm, because initially it was 30 mm, finally 10 mm, and this is the thickness we need to reduce. So we have maximum possible draft, delta H maximum equal to mu square into R. So for each pass we get the 3 mm thickness reduced as per these calculations. So to reduce 20 mm, we have, therefore we cannot reduce more than 3 mm in a single pass, but we have to reduce 30 mm minus 10 mm equal to 20 mm. So for each pass if we reduce 3 mm, for 20 mm it is 20 upon 3, that is nearly equal to 7. So we need to have the number of passes of 7 numbers. So option D, 7 is the correct option. A strip is to be rolled from a thickness of 30 mm to 15 mm using two high mill having rolls of diameter 300 mm. The coefficient of friction for unaided bites should be nearly. So we need to find the mu value in this question. So we have given diameter is equal to 300 mm. So thereby radius equal to 150 mm. Initial thickness 30 mm, that is here, and final thickness 15 mm, that is here. So once we put all the values, we get mu as 0.3 or something. So option A is the correct option. A 80 mm thick steel plate with 400 mm width is rolled to 40 mm thickness in 4 passes. So we have 80 mm thick plate which is being rolled to 40 mm final length, final thickness. The plate width is 400 mm in 4 passes. Equal reduction in each pass by using rolls of 800 mm diameter. The roll diameter is 800 mm. So the radius is 400 mm. Assuming the plane strain deformation, what is the minimum coefficient of friction required for unaided rolling to be possible? So we need to find the value of mu. So we know already maximum possible draft equal to mu square into R. So we have delta H value and R value. So for mu it is 0.3 or something. So thereby option D is the correct option. In a rolling process, thickness of strip is reduced from 4 mm to 3 mm. So the thickness initially it was 4 mm and then it is reduced to 3 mm using 300 mm diameter rolls. So the roll diameter is 300 mm. Rotating at 100 rpm, and it is rotating at 100 rpm. The velocity of the strip in meter per second at the neutral point is. So this is the neutral point. At this point, we need to find the velocity of the strip. So here, the velocity at neutral point is equal to the velocity of the roller, because there is no slip occur, because they are not mentioned any slip condition in this. So thereby neutral point velocity is equal to velocity of roller. So we have velocity equal to pi dn upon 60. So we know already diameter and 100 rpm. So we get the velocity as 1.57 meter per second. So option A is correct option. A mild steel plate has to be rolled in one pass such that the final plate thickness is two-thirds of the initial thickness. So the final plate thickness is equal to two-thirds of initial plate thickness with the entrance speed of 10 meter per second. So entrance speed V naught equal to 10 meters per minute and roll diameter of 500 mm. If the plate widens by 2% during rolling. So if the plate widens by 2%, so that is 2% compared to initial condition. So initial width plus 2% width. So that is here. Final width is equal to initial width plus 2% of the initial width. So here 2% is nothing but 2 by 100, that is equal to 0.02. So thereby this is 1 plus 0.02 B naught, so that is here. The exit velocity in meters per minute is. So here we need to find the exit velocity. The inlet and outlet volume rates of material flow must be same. So the volume flow for the inlet and outlet is same. That is here. Inlet volume flow, outlet volume flow, because H is thickness in meters, B is width in meters, velocity meter per second. So that we can write meter cube per second. So that is the volume flow. So this is for inlet and this is for outlet. Already we have given HF equal to two-thirds of H naught and Vf equal to 1.02 B naught and velocity at inlet is also given. So once we put these values, we get the Vf as 14.706 meter per minute. So 14.706 is the correct answer. In a single pass rolling operation, 200 mm wide metallic strip is rolled from a thickness 10 mm to a thickness of 6 mm. So width of plate is 200 mm, initial thickness 10 mm, final thickness 6 mm. The roll radius is 100 mm, roll radius R is 100 mm and it rotates at 200 rpm. The rotation is 200 rpm. The roll strip contact length is a function of roll radius and initial and final thickness of the strip. If the average flow stress in plane strain of the strip material in the roll gap is 500 megapascal, so the stress is 500 megapascal. The roll separating force in kilonewton is. So we need to find roll separating force F value. So we have roll separating force F equal to rho naught projected length into width, where projected length LP is equal to square root of radius of roll into maximum possible draft, that is here, and then width as it is. So we have stress given and then length is also given, and then maximum possible draft, sorry, this is radius and maximum possible draft, as well as width is given. So thereby value is 2000 kilonewton. So that is the answer. An annealed copper plate of 300 mm width. So copper plate of 300 mm width and 20 mm thickness. The initial thickness is 20 mm is rolled to 16 mm. So the final thickness was 16 mm thickness in one pass. Consider the radius of the roller as 400 mm. So the radius of the roller is 400 mm. Rotational speed 80 rpm, n equal to 80 rpm, and average flow stress during the rolling is 400 megapascal. Flow stress 400 megapascal. Calculate the true strain and rolling force. So we need to find true strain and rolling force. So we know rolling force F equal to rho naught square root of projected length LP, that is LP equal to square root of radius of roller into maximum possible draft, that is R square root of delta H into width of the plate. Since all the values are given, we get the force value as 4.8 meganewtons. Friends, these are some important formulas in rolling. The first one is delta H equal to D into 1 minus cos alpha, where alpha is bite angle, D is diameter of roller, and delta H is the final thickness of the plate minus, sorry, initial thickness minus final thickness of the plate. So let me call this as first formula. And then maximum possible draft delta H equal to mu square into R, where R is roll radius, mu is coefficient of friction between roll and work. And next formula is roll strip contact length L equal to R into alpha. Alpha is bite angle, R is roll radius. The velocity at neutral point is equal to the velocity of the roller. So this is only true when there is no slip occurs. Neutral point n is equal to velocity of roller, that is v equal to pi dn upon 60. Only there is no slip occurs. Roll separating force F equal to rho naught projected length into width. So we have projected length LP equal to square root of R into delta H, that is here projected length alpha equal to R into delta H. This is for projected length, this is for arm length, and for force, torque, and the total force. Thank you for watching the video.